Hello everyone and welcome to this lecture in the hands-on large language models series. Today we are going to learn about a very important concept, and that is the concept called as chunking. I wanted to cover this in yesterday's lecture or the previous lecture itself, in which we talked about dense retrieval and we saw a hands-on example in which we took a document base, we entered a query, and then we retrieved those documents or those sentences rather which matched well with the query. That's the spirit of the dense retrieval system, which we have seen in detail in the previous lecture. If you have not seen the previous lecture, I would highly encourage you to watch it to improve your understanding. So the reason I thought of creating this separate lecture is because the efficiency of dense retrieval really depends on your chunking strategy. So first let me quickly revise and recap what is dense retrieval through the example which we started, and then let us try to understand everything about chunking. So what we did in the previous lecture was we took a Wikipedia article on this movie called as Interstellar. So let's say this is our document base. These three paragraphs are our document base. So what we did was we went to the Google Colab code and we added these three paragraphs as text. Alright. Then came the important part. What we did was we took the text. So let's say this is the Interstellar. Let's say this is the Interstellar 3 paragraph text, right? What we did was we took the text and we broke the text down into individual sentences. Break into individual sentences. And then what we did was we stored all of these sentences in a list. So we maintained a list which I'm going to draw right now. So let's say this is the first element of the list, this is the second element of the list, this is the third element of the list, dot dot dot. Overall, I think there were 15 sentences which we had. So these were the 15 sentences. So if I would write, this is the first sentence, this is the second sentence, this is the third sentence, and 15th sentence. This is the list. And then what we did was we embedded each of the sentence into a vector of 4096. Let me check if that's correct. Yeah. We embedded each of the sentence in a vector which is 4096 dimension. So that way then we had a matrix, since all of these 15 sentences were embedded as 4096 dimensional vectors. So the size of this matrix which was there, this was 15 rows multiplied by 4096 columns. Alright, and then what we did was whenever you had an input query, let's say the query which we had was how precise was the science, right? So let's say this is the query. How precise was the science? Let's say this is my query. And then what we did was this query also was embedded into a vector. This query also was embedded into a 4096 dimensional vector, and then we found the distance of this vector with all of these vectors. And we discussed several distance metrics yesterday, including the Euclidean distance and the cosine. So we found the distance, let's say that is D1, D2 and D15. And then only those documents were returned whose distance was very less. So for example, we can choose that only return the documents with the least distances and return 3 documents. So then if D6, D9 and D12, let's say, were the documents with the least distance with the query Q, so let me call this Q, these were the answers. These were the documents which were retrieved, right? And these were the results which were shown. So if you look at the results which were shown, if the query was how precise was the science, if you print out the results, you will see that 3 results were shown. It also has received praise from many astronomers, Caltech theoretical physicists, and Interstellar uses extensive practical and miniature effects. And you see the distance, this is the distance of the document with the query. These 3 are the documents with the shortest distance. So among these, the first one has the least distance, then the other two have slightly larger distances. But among the 15 sentences, which I am also calling documents right now, these are the three with the lowest distance from the query, and that's why they are returned right now. Alright, so this entire workflow which I just described to you right now is called as dense retrieval. This is called as dense retrieval. And in the previous lecture, what we did was we focused on several aspects of this dense retrieval system. We focused on how to do this embedding, or which embedding models to use. Then we looked at different distance metrics. So we took a look at what really happened after we break down the paragraph into individual sentences, right? Today, what I want to do is I want to focus on this initial step itself. This initial step. Why did we take the 3 paragraph text and break it into individual sentences? Why couldn't we just break it into 3 paragraphs, let's say? Or why did we even need to break anything into small parts? So this process of taking a document and breaking it down into small parts is called as chunking. And chunking is an extremely important and crucial process because chunks are the smallest units of the document. So if you ask the question which document should be returned, actually you are asking which chunk should be returned. So the level at which we do the chunking will directly contribute to the results which are retrieved. Let me give a short example. Right now, if I take this whole text, let's say, and if I implement the first type of chunking, which is just take the entire document itself. Take the entire document itself as a chunk. Then you see what will happen. At least right now, when we do sentence level chunking, we have 15 chunks, right? If we take the entire document as a chunk, there will just be one chunk, and that chunk will be encoded as a 4096 dimensional vector, right? So whenever you have the query and you are looking at what's that chunk with the lowest distance from the query, there is only one chunk. So no matter what the query is, always this is the only chunk which is going to be given as the output. That is not what we want, right? So this is where we come to the different types of chunking systems. The first type of chunking is, as I mentioned, one vector per document. So let's say if you take these 3 paragraphs of the Interstellar Wikipedia and if you encode this entire thing as one vector itself, that's essentially one vector per document. And what this does is that if we use a single vector to represent an entire document, it leads to a highly compressed vector that loses lot of information in the document. So let's say if you are looking at this document, right, there is information about what the film is in the first paragraph. The second information is about how the film was shot, what are the digital effects, and the third paragraph has information about what was the impact of this movie in terms of revenue, and what is the accolades or what are the awards which this movie won. How can you represent this and all these 3 different things in one vector? If you represent all of this in one vector, it means that essentially you are compressing the information, right? That one vector now has information about the introduction, about how the movie was shot, and about how or what the awards the film won. So that's like putting too much pressure on one single vector, and unless the dimension of the vector space is very large, it is not able to capture all of this information. So if you do paragraph level chunking, or rather I should rather call it one vector per document chunking, it will lead to faster processing because the number of chunks which you need to compare the query will be less. So the computational time will be faster, but there is a huge downside to this. And the downside to this is that we really lose a lot of information which is present in the document, which is not what we ideally want. So I never recommend this strategy of chunking, whereas the better strategy is to chunk the document into multiple chunks. Now here also there are different ways of how to chunk it into multiple chunks, right? Currently what we saw in the code was we took every sentence and used every sentence as one chunk, right? There are different ways to do this. You can do paragraph level chunking, which means you can take this one paragraph as one chunk, this second paragraph as the second chunk, this third paragraph as the third chunk. So let us understand the different ways to chunk one document into multiple chunks. So in this approach, what is done is that we chunk the document into smaller pieces and then we'll embed those chunks, right? And there are different strategies to do this type of chunking as well. In particular, these strategies can be broken down into three parts. First, you can say that I want a chunk after every 15 characters. So instead of doing sentence level chunking, I can say that no matter where the sentence ends, I'll just look at 15 characters and that will be my one chunk. So that is called as character level chunking or character split. The second type of chunking is token split, basically, where instead of looking at characters, you say that I want to have a split after every token or after a certain set of tokens. So this is token level split. And the third category is token level split but with overlap. So let's take this example. Llama 2 was trained on 40% more data than Llama 1. If you split after every 5 tokens, the first chunk will be this, Llama 2 was trained on, and the second chunk will be this, 40% more data than Llama. You see there is no overlap between chunk 1 and chunk number 2. So in the third type of chunking, it's again a token split, but there is an overlap, which means that this on, which was the last token of the first chunk, is carried over to chunk number 2 right now. Similarly, this than, which was the last token of the second chunk, is now carried over to chunk number 3 right now. And if you try to see why is this done, the reason overlapping chunks is done is that it prevents the absence of context, which means that there is some context retained between chunks, and that's very important, especially when you are doing dense retrieval and you are retrieving documents which are relevant in meaning to the query. So this is illustrated here also. So what we did right now was a sentence level chunk like this we did in code right now. What I suggest you to do is that when I share this code file with you, you can do a paragraph level chunking, and it's easy to do that. See, currently we just split into sentences, right? You just take this whole paragraph as one chunk, this whole paragraph as the second chunk, and this whole paragraph as the third chunk. So this text list now, instead of having 15 sentences, it will just have three paragraphs. So it will have just 3 elements, which we will compare the query with. So you can try this. And the third is overlapping window of sentences, as you can check over here. So instead of just taking separate paragraphs, we do overlap between different chunks. So see, the yellow chunk and the green chunk here are overlapping, right? This much is the overlap. And as I told, overlap is good because then it retains the context. It prevents the absence of context rather. So let us look at the advantages and disadvantages of each types of chunking. What is the type of chunking you should do and when should you do it, right? So if you look at sentence level chunking, right? The problem with sentence level chunking is that it does not capture any of the context at all. So for example, if let's say I'm looking at the third paragraph, right? Or let's say if I'm looking at the second paragraph, and if I do sentence level chunking, I see that here the original script was to be directed by Steven Spielberg. That's what I get in the first sentence, and that's it. That's all the information in the first chunk. But all the rest of the information is kind of lost, right? Like theoretical physicist Kip Thorne was also an executive producer. And maybe these two sentences, it's good if they are contained in one vector because they are kind of related to each other. So that is what is meant by loss of context. If you do chunking on very small units, then there is no context retained between chunks. So, and the importance here is that if let's say there are 3 sentences which are connected to each other, right? And if each of these are encoded as separate chunks, when you ask the query, ideally all 3 should be returned because all 3 mean the same thing. But if you have chunked those into separate chunks, then only one of them might be returned. So to give you an example, let's take a simple example of Harry Potter, right? So if I write Harry Potter wore glasses, then let's say I write Harry Potter had a scar on his face, and let's say I write Harry Potter's height was 5 foot 6 inch, let's say, for an example. Now let's say if these three are my documents, and in case 1 I've encoded them as separate chunks. So let's say this is chunk 1, this is my chunk 2, and this is my chunk number 3. And if the query which I am asking is, let me mark it with different color. If the query is how was, or describe Harry Potter's appearance. Now if you say describe Harry Potter's appearance, right, and if I've chunked all of these as different chunks, maybe this chunk has a distance d1 with the query, this has a distance d2, and this has a distance d3. So out of these, maybe d1 is the smallest, so only d1 will be returned. So only d1 will be returned as an output. But that's not correct, right? Because describe Harry Potter's appearance, if that's the query, ideally all three should be retained. But the problem which has happened right now is that we have chunked all of them into different chunks. So only one chunk can be returned at a time. So one way to get around this is simply to encode all of these as one chunk. To encode all of this as one chunk. So that way, when you say describe Harry Potter's appearance, this entire chunk will be given to you. So you see there is a trade-off between having granular level of chunks versus having big chunks. If you have granular level of chunks, more specific information is retained, but context is also lost. Whereas if you have big chunks, then specificity is lost a bit, because everything is merged into one vector, but more context is retained. So that is the trade-off which you always need to consider when deciding whether you want sentence level chunking or paragraph level chunking. I think the best way to go about it is to have a best of both worlds, right? Instead of having one chunk, let's say, instead of having one chunk or three chunks, why don't you do overlap between chunks? So what that means is that, let's say the first sentence along with few of the second sentence is the first chunk. Then if you do the second chunk also, let's say, has an overlap. So let's say the second chunk is this. So you see now if you look at the yellow and the green chunks, there is an overlap between them, which is good, which means at least some amount of context would be retained and specificity would also be there. We are not bucketing the whole thing into one chunk, but we are kind of having an overlap. So that's the third thing which I have mentioned here. This is overlapping window of sentences. And this is extremely useful because some chunks derive a lot of meaning from text around them. That's why overlap between chunks can be very important to prevent loss of context. So let's say Interstellar, right? And if you are asking what is the revenue, and here it's mentioned $681 million. Let's say 2 sentences later, it's again mentioned something about the revenue. Now, if you are doing sentence level chunking, you will lose that second part because only the first sentence is captured as an individual chunk. This is what is meant by loss of context. So this overlap method, basically I call it the overlap method or overlapping window of sentences. It prevents the context from being lost. So here you can see a separate section has been given to overlapping segments. So chunking the text into overlapping segments is one strategy to retain more of the context around different segments. So here if you zoom in, you will see that the yellow green have an overlap. The green chunk and the red chunk also have an overlap. This is so that we retain some context between the different chunks. And then the process is the same. We use an embedding model and we convert each chunk into a vector, and then we compare it to the query vector and choose the chunk with the lowest distance. Alright, so I hope until this part you have got a decent idea regarding chunking strategies and which chunking strategy should be used when, what are the advantages and disadvantages of different chunking strategies. So all of these chunking strategies have been borrowed from this book Hands-on Large Language Model by J. Alamar. But later I discovered that there are few more chunking strategies as well, which earlier I had not looked at. And let me actually show my screen now. These are the chunking strategies which were first described in a blog post by Avi Chawla. So if you look at these are five different chunking strategies, right? Let's go through them sequentially to complement our learning about different chunking strategies we have learnt until now. So the first chunking strategy mentioned here is fixed size chunking. So here we already decide the size of the chunks which we want. So this relates very well with all of these actually. If you want to split every 15 characters, if you want to split every 5 tokens, if you want every 5 tokens with one overlapping token, if you want every one sentence to be token, as we did here, if we want sentence level tokenization sentence level chunking, all of these come under the category of fixed size chunking, where we already decide the chunk length which we want. The second type of chunking is also called as semantic chunking. What this means is that you start with the first chunk and you keep on adding new segments. You keep on adding new segments to this chunk until the cosine similarity drops drastically. So what this means is that, let's say you add this first chunk, then you add the second chunk. If you're looking at just one chunk, you add this sentence, you add this sentence, then you add the third sentence, and you're always comparing the cosine similarity. Now if you come over here, maybe the cosine similarity drops drastically. So then you mark the end of the first chunk and you start the second chunk. So this is called as semantic chunking, where essentially you are doing chunking based on the meaning, right? When would cosine similarity drop? When the meaning of something which you are considering right now is not very much aligned with the meaning of something which has come previously. So essentially, if you do semantic chunking, all the sentences in one chunk will essentially have similar meaning. This is an amazing way to deal with meaning and to make sure that chunks capture meaning. Currently what we are doing, if you see in sentence level chunking, we are not capturing any meaning, right? We are just looking at each sentence and then making it as a separate chunk. That's why I think semantic chunking is very powerful. The third type of chunking is called as recursive chunking. Now in the recursive chunking, what's usually done is that we select a segment and we keep on adding more segment or more sentences until the size is reached. So let's say for example you have a document, right? And if you already grouped them into chunks, now if you're looking at an individual chunk, let's say you're looking at this chunk and you see that its size is very large, then you again break it down into smaller chunks. And if you look at maybe here also, if the size of the chunk is very large, you break it down. And now if you look at each of these chunks and see that again the size of this chunk is very large, then you again break it down into smaller chunks. So that's why it's called as recursive chunking. So the recursion part comes because we are again doing splits based on the size. So once you do this entire process and once you look at each of the chunk now, if you look at each of the chunk in the leaf, you will see that all of these are less than a particular size. So this will make sure that the chunks do not become very large, because very large chunks lead to loss of meaning. So that's recursive chunking. The fourth is very simple to understand. It's document structure based chunking. So essentially if you have a document which has a title, introduction, section 1, section 2 and conclusion, what you essentially do is that you will put the title as one chunk, you will put the introduction as the second chunk, you will put the section 1 as the third chunk, section 2 as the fourth chunk, and you will put conclusion as the fifth chunk, let's say. So that's fourth, which is document structure based chunking. And the fifth type of chunking is large language model based chunking. So here you don't do anything manually, you don't prescribe an algorithm for chunking. You just give the document to the large language model, and the large language model itself understands the chunks, or the large language model generates chunks on its own. So this is the this is the fifth method of chunking, which is called LLM based chunking, right? So essentially we have looked at 5 types of chunking in this post. First is fixed chunking. So either if you already decide I want to chunk at one sentence, or let's say after 5 words or after 15 tokens, you are deciding what you want to chunk before itself. That's fixed chunking. The second is chunking based on meaning. So you will put everything in one chunk has to be of similar meaning. Everything of another chunk has to be of different meaning. So the way to do this is that you initialize the first chunk and you keep on adding more sentences or segments to that chunk until the cosine similarity becomes very low. So if there is a new segment whose cosine similarity does not match, it goes to the next chunk. The third is recursive chunking, which basically the best way to explain it is using something like this. You first do the chunking. If the size of some chunk is greater than a particular value which you already have to decide, then you do the chunking again. And so the chunking continues until all the chunks are less than a particular size. That's recursive chunking. Fourth is document based chunking or document structure based chunking, where you look at a document, let's say it has title, introduction, section 1, section 2, conclusion. Each of these will be a separate chunk. So the title will be a separate chunk, the introduction will be a separate chunk, section 1, section 2 will be separate chunks, conclusion will be separate chunk, let's say. And then the fifth method is the large language model based chunking, where the LLM itself does the chunking. Until now, you see, you have already decided how you want to do the chunking, right? In all of these. But in the fifth, you don't specify anything. You let the large language model take care of doing the chunking on its own. Of course, you will need to specify prompts related to what you want the chunking to look like. I'll share this link in the information section so that you can go through these strategies in more detail. But that brings us to the end of today's lecture, where I wanted to devote a separate lecture to chunking. So now chunking leads to a more expressive search index than representing the entire document as a vector. This is very important. We cannot represent this entire thing as one vector because we completely lose information. So one way to look at chunking is that it leads to a more expressive search index than representing the entire document as a vector. Now the authors of this book, Hands-on Large Language Model, let me show that. Yeah, the authors of this book, Hands-on Large Language Model, they have written this, that expect more chunking strategies to arise as the field develops, some of which may even use LLMs to dynamically split a text into meaningful chunks. So this was actually the fifth method which we looked at, LLM based chunking. But what I want to highlight here is that in these videos I always try to highlight areas where students can do active research, right? So this is an area of active research. So this can be an area of active research, which means that this is an area where people are working, but there is scope for a huge number of advancements in the chunking strategies. So if you are looking for novel problems to work on, just take small amount of text and think creatively of some chunking strategies which you can come up with. So for example, if you want to do more research in any of these, let's say semantic chunking, go for it. Read papers which have been published in this field, and if you feel there is a gap somewhere, try to fill that gap by doing studying or research yourself. All of these code files will be available to you. I'll share them with you so you can use all of these as a reference to begin your research. So thanks a lot everyone. This brings us to the end of this lecture on chunking. Just keep in mind that I am aware of big companies or startups who are struggling with chunking. So these companies or startups have tasks of analyzing text, let's say, or retrieving the best possible text given a query. So all of them need to use documents, and all of them need to convert these documents into embeddings. Right? Now the challenge is that there are embedding models to convert documents, but the problem is that what to embed, that's the bigger question. Whether I will embed individual sentences or whether I will do paragraph based chunking. So that's where chunking comes into the picture. We know how to embed, but companies and startups are struggling right now with what to embed. And this question of what to embed is where the design choice of a machine learning engineer or a large language engineer comes into the picture. Thanks everyone. I hope you learnt a lot from this lecture. I'll share the code file with you which I'm showing right now, and I'll share all these links also with you. Thanks again, and I look forward to seeing you in the next lecture.